Okay, hello. So, what today we'll discuss with you. Today I'll discuss with you about electric dipole and two positions. For two positions, like on axial position and on the equatorial position, we'll calculate the field due to electric dipole. Okay. So the first, let us discuss what is a dipole. So as you can see here the definition, the electric dipole is a pair of equal and opposite point charge. Okay, so it's a pair of equal and opposite charges q and minus q separated by a small distance, very small distance. Let's say the distance between them is 2a. Okay, suppose there are two charges, one is plus q, another charge is minus q, and they are separated by a distance, let's say 2a is a distance between them. So this forms a, together the two charges, they forms a dipole, and this situation is created many times in an in you can say atom, or you can say in polar molecules. In chemistry you have learned polar molecules. So polar molecules are the molecules who had some dipole moment. The dipole moment is not zero. Okay, so that means, suppose for example, if there is an atom, and you know in an atom the nucleus is there at the center, and in the nucleus the electrons, the protons are there and neutrons are there. Neutrons are chargeless and proton has positive charge, and electrons are revolving around, or electrons are in different cells. Electrons are revolving around the nucleus in different cells. Okay, so if near the atom, if some positive charge cloud will be there. Okay, so positive side of a, or delta plus, you can say positive side of the some another atom or molecules will be there, then what will happen? All the electrons will be attracted towards this positive charge cloud, and this will create a situation like this. So that means your nucleus that will have positive charge will be in one side, and all the electrons, those who are were revolving around the nucleus, they will be on another side. Okay, so all electrons will be they will be at one place, and the protons will be at one place. It means they will be separated. Okay, and there will be some distance between them, so they will, means this situation they create a dipole. And you know that in an atom number of protons is equal to number of electrons, so we can say that here it has created the one dipole case. Okay, so it will have some moment, dipole moment, that will calculate now. Okay, so this situation or this type of situation is created by a dipole. So now you understand that here also it is a dipole having equal negative charge and equal positive charge. So here what we'll do, we'll calculate the dipole moment, or we can say first we will calculate the field, then we will write the field in terms of dipole moment. Okay, so first let us calculate the field due to this dipole for the points on the axis, Okay, so we'll calculate first the field. We'll calculate the field of this dipole. The field of an dipole, the electric field of an dipole for the points on the axis. Okay, so we'll basically calculate for two cases. So this is case 1. The electric field will calculate for the points on the axis. So points on the axis means, which is the axis? The axis is which join two center of the charges. Okay, so two charges plus q and minus q are separated by a distance 2a. Now they are the line which joins both the charges are the axis of the dipole, and let's make it expand this line. Okay, now we'll calculate the electric field at any point p. We'll calculate the electric field at any point p on this axis. Okay, so how will you calculate? So let us calculate. As you know, as this is a positive charge and two charges are separated by a distance 2a. Okay, so what will be the electric field due to plus q charge? Because each individual charge will create a field at point p. So the charge plus q will create an electric field outward. As you know, electric field due to a plus charge is outward in nature, that we have discussed in the field lines. So this is a plus charge, the field lines will be outward in nature. Okay, and due to a negative charge, the field lines are inward in nature, that we have discussed in the field line cases. Okay, so here due to this plus charge, that will be electric field will be plus q, that will be away from the plus q charge. Now due to this minus q charge, there will be electric field towards minus q charge, that will be inward. So this will I'll write E minus q. Okay, now what will be the total electric field at point P? Just sum of this E plus q and E minus q. This is very simple. Okay, just we will add two vectors E plus q and E minus q, and we will find out the result of the electric field at a point on the for the points on the axis of the dipole. Okay, so let's consider the midpoint of this dipole is called the center of the dipole, and so if this is a center, then it will bisect this line from q to plus minus q to plus q. So here it will be a, here it will be a, it will become half. Okay, so now one more thing is that the direction of the dipole by convention, I am saying you, the direction of the dipole by convention is from negative to positive charge, is from negative to positive charge. So here one negative charge is there, here one positive charge is there. So dipole direction is, let's say it's p cap, we represent with dipole with p cap, and it is from negative to positive. This is by convention, right? So now let us write down the electric field due to plus q charge and minus q charge. So what will be the electric field due to plus q charge? So let us write down. So electric field due to plus q charge, let's write the magnitude. So what is the electric field? Electric field by definition it is 1 by 4 pi epsilon naught. Due to plus q, it is plus q by, we are writing the magnitude only, it will be q by, what will be in the denominator? R square. R is the distance from this plus q to p. What is the distance from plus q to p? So we will use from the center to p, the distance is r. We will consider from the center to p, the distance is r. Okay, so if from p, if from the center to p the distance is r, then what will be the distance from plus q to p? Now r minus a, isn't it? So it will be r minus a whole square. So magnitude, I am not writing the direction, I will write the direction at the end. So now E minus q will be what? E minus q magnitude will be same, not same, 1 by 4 phi epsilon naught. Charge is magnitude is q. What is the distance from minus q to p? Now p to center is r. From here to here it is r. Now from center to minus q is a. So what is the total distance? R plus a whole square. Clear? Now these are the two electric field we got at the point P. Now we'll add them up. Okay, we'll add them up and we'll find out the total electric field. Okay, so how will do it? So that to calculate the total electric field, let us do it. Okay, so you just see. Okay. So the total electric field, E will be equal to E plus Q magnitude plus E minus Q magnitude. This will be the E magnitude. Okay, and the direction will be, we'll consider the direction. Okay, if we want to write down with the direction, so the direction is, you can say, the minus Q is along the plus Q, E plus Q is along the direction of P, and E minus Q is along the direction of opposite minus P. So we will write in vector form that E will be equal to E plus Q, that is 1 by 4 pi epsilon naught Q by this one, Q by R minus A square. E plus Q is equal to Q by R minus A whole square. So as I told you, for plus Q, the direction is in the same direction of P cap, that is the moment, your dipole moment vector. So I'll write this is P cap, and for this one, E minus Q, it will be 1 by 4 pi epsilon naught Q by R plus A square, and the direction is minus P cap, because as I told you, E minus Q direction is opposite to P cap. So I'll write this is minus PQ. Now what will be the common? The common is 1 by, what are the common? Common is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. Then Q is also common. Q will come outside, and inside is 1 by inside is 1 by R minus A whole square. This is minus is there, so minus 1 by R plus A whole square bracket and P cap. Or you can write this is Q by 4 pi epsilon naught. What will be the LCM? The LCM is R minus A whole square, R plus A whole square. Okay, so if you divide this, this will get R plus A whole square minus R minus A whole square P cap. Now you can see A plus B whole square minus A minus B whole square. What is the result? It will be plus 4AB. So you can write this one, Q 4 pi epsilon naught. We'll use these two identity. One is A plus B whole square minus A minus B whole square is what? This is 4AB. Okay, and one more identity we'll use, that is A plus B into A minus B is equal to what? A square minus B square. These two identity we'll use. So it is R plus A whole square minus R minus A whole square. This will give you 4RA divided by, in the denominator, what we will write? In the denominator we will write that is R minus A, R plus A, that means, and square is there, so we will write R square minus A square whole square is there, P cap. So this is your total electric field, okay, at the point P on the axis, Now what we'll do, as you know, A is a small number. I have told you the distance between two charge is a very small number, in the order of maybe 10 to the power minus 3 or lesser than that, 10 to the power in nano also. So or nano femto also it's possible. So what it will be, so A square will again a small quantity, because square of the decimal number or fractional number will be another small number smaller than that. So we can say A will be very small as compared to your R. So we will write R is greater than equal to A. So we will neglect A square. Okay, so when we will neglect A square, what we will write? A by Q by 4 pi epsilon naught 4RA, this will be R square R to the power 4 p cap. So R square will cancel, Q will be left. So what is the result? Your E is equal to, okay, Q into 4A by 4 pi epsilon naught p cap. This is RQ, okay, 4. Or I can write, or I can use one dipole moment vector. What is dipole moment vector? Dipole moment vector will define Q into 2A is that Q is the one, either one charge into the distance between them. P cap is P vector. This is called dipole moment vector. This is called dipole moment vector. Okay, so now what we'll do, just will represent in terms of your dipole moment vector. So E will be equal to, in terms of dipole moment vector, you can keep it here in the exam. If the question is asked that write the electric field at a point due to the points on the, for the points on the axis of a dipole, okay, the field is this one, or represent the field in terms of your dipole moment vector, then you will do this step. So here I can write Q into 2A, so it will be 2 Q2A p cap will become P vector, or let me write in this way, 2 by 4 pi epsilon naught. I am not cutting it because 1 by 4 pi epsilon naught, you know, is value, good value. There is 9 into 10 to the power 9, so I am not, that's why keeping it like that. So this is E vector will be 2 by 4 pi epsilon naught P by RQ. Okay, so this is the result of your electric field on a point on the axis of a dipole. This is the total net electric field at a point at a distance r. So but you should note that here, you know, electric field generally for a point varies in forms of 1 upon r square, okay, but due to a dipole at a distance r, the electric field decreases in the form of RQ. That means it's more stiffer, it decreases faster than a single charge, okay. So this is also one important result of this one, okay. So in the next class, next video, I'll discuss about the electric field due to the points on the equatorial plane. Thank you for watching this.